LPG gas, and you have seen lot of accidents happening all over the world because of this LPG. So now this is a particular silicon chip, and on the top of the silicon chip, we have a coated material. Now as you can see here, a coated material, and then you have there is no coating from the other side. You can see the dimension of the coated material is also almost 500 micrometer, which is almost half of the millimeter. Now, what happens in case of gas sensors? Like you have oxygen sensors, you have hydrogen sensors, you have LPG sensors, and then all those other toxic gases which can be sensed. So the point is that you need to identify the material that can be actually make some like change in the resistance or change in the structure of that material because of the presence or the absence of the gas. So like we have an LPG. So if there is an LPG sensor and on the material X, the resistance of the material X changes as the quantity of the gas increases. So that particular material X can be coated onto this sensor, and then it senses the gas. So if there is a very low gas presence, the output current may be zero. And if there is a lot of gas, if the gas leakage is very high, then the current will be. So in that particular applications, these gas sensors can be employed. And now why we have a gas sensor, as if we have all kinds of sensors in this world, but the typical difference between these sensors and our previous sensor is that these are in micro dimensions. And when you go down to like millimeter, micro, and nano, and quantum, so generally the properties of these atoms and molecules changes. So as you must have heard about the Newton's law. So there are three laws of Newton's. But when you go to the nano dimensions, or below nano, or like pico dimensions, then these laws of Newton's are not applicable. So these microparticles or nanoparticles, they have their different physics, and they don't follow the physics which is as described by the Newtons, or which is available for bigger dimensions. So it is called as quantum physics. So therefore, when we go down to the micro dimensions, then we have another set of different problems which we have to take care while coating these materials. So it is not simple like I take a 1 meter, let us say, sensor and then convert it into 1 micrometer. So it is not that simple, as you only scale the dimension from 1 meter to, let us say, 1 micrometer. Now, another most successful application is this inkjet printer head. Now, in this inkjet printer head, you can see there is a nozzle here. This is a nozzle, and on the top of the nozzle, there is an ink reservoir. And on the top of this ink reservoir, we have a piezoelectric material. So, this is orange color is a piezoelectric material which is coated onto this ink reservoir, and then there are connection electrodes. Like one is connected to this yellow electrode, and the signal is connected to the orange electrode. So we have an upper electrode, and then we have a piezoelectric. Now what happens whenever, depending upon whether I want to print a dot or I don't want to print a dot, so the signal is then applied to this piezoelectric. So whenever I apply a small signal to this piezoelectric material, this piezoelectric material, okay, as we have seen in the pressure sensor, what happens is whenever there is a pressure applied onto this piezoelectric material, there is a change in the current. Now, whenever I apply the current here, there is a bending effect which is seen. And because this particular piezoelectric material bends, it pushes a small drop of ink out of this metal. So, a precise control of the ink can be seen using this MEMS application, inkjet printer head. And therefore, now you can see that inkjet printers are now almost printing 10,000 pages per one small bottle. So this inkjet printer head using MEMS technology was developed by HP, and therefore this is also one of the most successful application of MEMS. The another successful application of MEMS, which is coming up, is the portable blood analyzer. Now, as you know, portable blood analyzer, if you want to find out the RBCs or if you want to detect a malaria or something else, then you have to pass on some kind of different materials or reagents. So you can see here, there are two inlets, and these two inlets are used, one for blood and another for injecting some other reagents. Right? Now, there is a supply is applied between these two, and in this case, like which is shown here, injected and then you have a blood sample. So there is a mixing of the reagents and the blood here. So there is a mixing of blood and the reagent here, and then based on this mixing, then you can find out what are the RBCs or WBCs or a cancer or whatever it is. Right? So this another now right now this portable blood analyzer is under research, and not such is available in the market for sales. But now portable blood analyzer are also being like researched by different scientists using MEMS technology. So from this, there is another field which is coming up, which is what you call that as a something. I am not getting that name right now, but I will let you know. So through this fluid mechanics. So fluid mechanics is actually coming into the picture here, and another branch of MEMS now it is being thought of, where you can measure the flow rate, you can measure the and all other parameters which are associated with the fluid mechanics. I'm not aware about those fluid mechanics as such, but so this is also one of the great applications. Now, let us come to RF MEMS, radio frequency MEMS. And as you know that radio frequency, uh, so because we are, most of them are electronic student here. So now because of IoT, you know that like you have GPS connection, you have Bluetooth connection, you have Zigbee, then you have LoRa protocol, and then now there are so many protocols are coming up, and then you have satellite communication and whatnot. So now, and we'll talk about this in detail after the few minutes. So you required radio frequency electronic components such as capacitors, you required inductors, and you required filters. Now, why this radio? Why it is so? Where you can apply this RF MEMS technology is, you can see like you have satellite communication, then you have antennas, you have LAN, wireless or wired LAN connections, radar system, and then our mobile phones, RFID tags, automobiles, everywhere. So as in now, when you see like all these will be connected through IoT, your automobiles will be connected, your satellites and your refrigerators and televisions and everything will be connected. So whenever all of these things will be connected, even though it will be connected through wireless communication, but at the end, at the back end or what you call, you need a sensors and you need a devices which will actually work. Like you can see here in case of automobile, it is 77 gigahertz application. So you need a electronic components which will work at such a high frequencies. And traditional components, like traditionally you have resistors, capacitors, and inductors. Traditionally, these components are not able to work at such high frequencies. So the basic problem, like if you can see now, since last so many years, we haven't seen a processor from more than i7 processor, and it has stuck up to 2.4 gigahertz from last so many years. When we started with 8085, which was at 3 megahertz, maybe around 1975, and around 2000 or 2010, we reached up to i3, i5, i7 processor with 2.4 gigahertz. So almost with a span of 30-35 years, we reached from 3 megahertz to 2.4 gigahertz. And beyond that, you can see it is becoming very difficult to make such a high speed app. So that is a now becoming an issue. And when we talk about transistor technology, 180 nanometer, 90 nanometer, 14 nanometer, and 12 nanometer technology. So now going beyond 12 nanometer technology is also becoming very difficult, because now it is almost to the almost to 1 or 2 atom level. Like if I go to 12 nanometer, there are hardly 4 or 5 the silicon bonding, silicon atoms are present. So then if you go below this, then you need to cover nanotherapy and then quantum physics. So the point is that here, so now people are looking after the MEMS systems, MEMS devices, and where traditional filters, traditional capacitors and resistors cannot be used, where we have frequencies 2.4, 5.2, and 30 gigahertz and 70 gigahertz. And in case of satellite communication, it is in terahertz. So now being talked about the applications of MEMS and applications of RF MEMS, let us see in brief how I can manufacture this or how I can fabricate the MEMS devices. Now, traditionally, there are three different methods which we can use it for the fabrication of MEMS or any electronic circuits. So this is the first one is the bulk micro machining. Bulk micro machining is like a it is like a murtika. In Marathi, we call it the person who makes the idol of gods and all. So he uses his chisel or some kind of different tools, and then carves out the particular model from the wood or maybe from the let us say stone. So similar method is applied here. In this case, we have this as a silicon chip. So this is a silicon chip, and from this silicon chip, the material is etched out. So from this, you can see this is etched out, removed. Then the silicon from this particular portion is removed. So once I remove this, or I can carve out this material, then it forms this kind of structure. So you can see here now this becomes a like a diaphragm, where the diaphragm there is a cavity here, there is a air space here, and it forms a thin diaphragm here. So if I apply the pressure onto this diaphragm bend like this, and I can use this as a piezoelectric material, and then I can find out the pressure. So these kind of like pressure sensors were designed using this bulk micro machining technology. But now the problem with this bulk micro machining technique is that whenever I want to etch the material from this particular area, you can see that because of the atomic structure of silicon, which is 100 or 111 or 110, then you can see that it doesn't etch in the vertically exactly 90 degree. It doesn't etch in 90 degree. So it is etching like in this trapezoidal fashion. So this is the disadvantage of using different etchants whenever I want to remove silicon, or let us say I want to remove metals on any other. Then this is the first disadvantage. Second disadvantage of using bulk micro machining is that basically I can form a single layer structure. Like if I want another structure on the top of this, then this cannot be done using bulk micro machining. Okay, or using some methodology, even if I do with the second layer, but then the third layer and the fourth layer and the fifth layer, then it becomes very difficult. So therefore, bulk micro machining is typically used only in case of single layer applications. Now the next method we have is a surface micro machine. So surface micro machining, the technique is similar to what we have in building of our houses. So we have a plinth, then we have the pillars, then we have the slab, then again the first ground floor, then again first floor, and then second floor and third floor, and so on. So that kind of technique is applied in case of surface micro machining. So here, what you have, here you have a silicon chip, and on the top of the silicon chip, standard oxide such as silicon dioxide or silicon nitride is deposited. Now, why we have a silicon nitride or silicon oxide deposition is because this is a silicon, and if you have a N-type silicon or if you have a P-type silicon, then you know that N-type and P-type silicons are conducting material. So if I don't have an oxide, which is an insulator, then the top portion and the bottom portion will be conducting. So if you have a metal here and there is no oxide, and then there is a p-type or n-type semiconductor, then it will start conducting and it will form a diode here. As you know that metal and semiconductor will form a diode. Okay, Schottky diode. So we and our application, we don't want to have a diode here. So therefore, there is an insulator is deposited onto this, and now now depending upon the structure that I want to fabricate, right? So I remove this particular oxide from this, and from this portion and from this portion. So this is done through lithography. So I will talk about lithography later in my presentation. Then on the top of this, I have deposited another material. It may be metal layer also. Okay. So the metal is deposited on this, and you can see this is a metal. And now, after the metal is deposited, this oxide is removed. Now, if I remove this oxide, then it forms this kind of hanging structure. So I can design or I can fabricate a hanging structure. Now I can apply same method. So on the top of this hanging structure, I can deposit oxide, I can remove this oxide, and I can have another metal layer. So on the top of this metal layer, I can have another second hanging metal layer. I can have third metal layer, I can have fourth metal layer, and so on. So such different multi-layered structure can be designed using surface micromachining. Then we have another process which is called as a Liga process, and where it is again our previous traditional process of making molds. So you can see here, this is a mold which is designed by. So what you have is a base, and then you have a photoresist, and in this photoresist you remove this photoresist. You remove the way you want to design the structure, and then you deposit any metal. So here it is shown as nickel metal. So you can deposit any metal or you can deposit any other material you desire. And once it settles down, you can remove this. So this is a standard process of like mold making or something like that, which is also used in design of MEMS devices. So you can see high aspect ratio and three-dimensional devices. Single layer, again, this is a single layer device, can be designed using this Liga process. But almost more than 90% of the times, surface micro machining is used, and all integrated circuit, transistors, diodes, and whatever integrated circuits you have, op amps, microprocessors, everything are designed using this surface micro machining. So now let us come to the IoT based RF MEMS, RF MEMS devices. Now, as I told you about, why do we require RF MEMS devices, and especially in IoT applications. Now, as you can see here, there are multi-standard and multi-band wireless communication systems. Now, when I talk about multi-band, is like I have a GSM. Now, in case of GSM, there are different bands. Means I am using a service such as only GSM, but in GSM I have different bands. As you know that we have mobile pockets, and every pocket is an hexagonal. The what you call an area is an hexagonal, and from one hexagonal area to another hexagonal, or to third one and the fourth one, there is a slightly difference in the frequencies, and even the technology is same GSM, but there is a change in the frequency. So we call it as a multi-band wireless communication system. Now, when I talk about multi-standard, multi-standard is like I have a change in the protocol, or I have change in the entire structure, like from GSM to Bluetooth, or from Bluetooth to Wi-Fi, Wi-Fi to Zigbee, or Zigbee to LoRa protocol. So what is happening? They have their they are different standards. They have different protocols. They have different methodology, error corrections, and securities, and everything are different. So now, if I want to have a IoT devices, this multi-standard and multi-band. So when I want to connect a refrigerator, televisions, and air conditions, and fans, and tube lights, and whatnot, and two-wheelers and four-wheelers, and everything, then it is not possible using only single wireless communication system. Like if I say I will use only GSM, I will not use Bluetooth, or I will not use Wi-Fi or something like that, then it becomes very difficult. And when we have lakhs and crores and 10 crores and 100 crores of devices connected on the internet, then you can imagine what is going to happen. So the problem is that I need different systems. Like I have different standards. I have GSM, I have Bluetooth, I have Wi-Fi, I have etc. I have Z, I have A, everything I have. And my system needs to support all these multi-standard and multi-band wireless communications. Now, when I talk about everything I need to have on a single portable device, then miniaturization. So, miniaturization is very important. That is, it should be small, it should be high speed, it should consume very less power. That means it should be miniaturized. Transceiver is transmitter and receiver. So, when I have an IoT device, then it should receive the signal and it should be able to transmit the signal. So in short, it is called as transceiver. So miniaturized transceiver are essential in wireless communication system for higher data rates and low power consumption. Now, in this particular figure, I have shown you a diagram which is a multi-standard or a multi-band transceiver. Now, see, on this particular portion, on this side, you will have a digital electronic circuits, and we are not interested in digital electronic circuit because it will be like any kind of processor such as Snapdragon or something else. We are interested in this analog part, which is the modulation, demodulation part. So you can see here there is an antenna, there is a tuning network, and then there is a switch. So this switch basically connects the transmitter and the receiver. So here you have a transmitter and here you have a receiver. Okay, and then you have a demodulation, and then you have a IF MEMS filter, intermediate frequency. As you know that when you whether it's a frequency modulation or it is a let us say amplitude modulation, and if it is amplitude modulation, then you have a super heterodyne receiver. So super heterodyne receiver converts the up frequency into the intermediate frequency, and then this intermediate frequency is then demodulated. So standard modulation and demodulation. So see, this is a actually analog portion. So in your mobile devices, we have an analog part and then we have a digital part. So digital part, you know, it's a Snapdragon or any other processor, but this analog part is very important, and this cannot be converted into digital part. So even though there is a digital communication, digital modulation or a digital demodulation, but there is analog modulation and analog demodulation. Now, let us take an example of your mobile phone. So, in your mobile phone, there are typically three applications. You have a GSM, you have Bluetooth, and you have Wi-Fi. So, let us say you have a GSM which is working on 900 megahertz or 1 gigahertz. You have a Bluetooth which is working at 2.4, and then you have a Wi-Fi which is working at 5.2 gigahertz. So now, as you know that from the standard or a conventional electronic components such as filters, and how I can design a filter is using the L. L means inductor and C means capacitor. So series parallel combination of inductors and capacitors are used for design of filters. Now, so depending upon whether it is a what you call it as a first degree, second degree, or you call it as a first order, second order, third order, fourth order filter, you know the filter characteristics and everything. So the basic problem is that I need three filters. So you can see here, this is a filter for GSM, this is for Bluetooth, and this is for Wi-Fi, and this is the receiver section. And then on the transmitter section, again you have for GSM transmitter one filter, then you have for Bluetooth another filter, and then you have for Wi-Fi. So depending upon receiver and transmitter, different filters are required for different applications. Now, why I cannot use a single filter instead of all these three, I cannot use a single filter is because I cannot tune my, let us say, LC components right from 1 gigahertz to 2.4 gigahertz and from 2.4 gigahertz to 5.2 gigahertz. So the tuning, such a wide tuning of 2.4 gigahertz with an interval of 2 or 1.4 gigahertz is not possible using your standard conventional inductors and capacitors, which are there inside your mobile phones. So therefore, what is happening is now, uh, even though other amplifiers can be same, switches can be same, demodulators can be same, but filters are different. So now the problem is, if you want to replace these three filters using single filter, then answer is this MEMS technology. So using MEMS technology, you replace or you can tune from 1 gigahertz or 900 megahertz to 2.4 gigahertz, from 2.4 gigahertz to 5.2 gigahertz. So therefore, now as you know that even though our mobile phones, the technology is very fast, it is like improving very fast, but our mobile phones are not becoming very slim and less powerless. So you can see our mobile phone, the size of our mobile phone has increased. So 10 years back, those mobile phones coming from the Nokia were smaller than what we have right now. And this is why is because the electronic circuit has increased number of times. So where you require single electronic circuit, now you require three electronic circuit to have all these applications, Wi-Fi, Bluetooth, and GSM on your mobile phone, and then you have other things also there. So the problem is that this circuit we want to replace with this circuit, where instead of three filters, we have only single filter. We have a tuning network. Instead of three power amplifiers, we have a single power amplifier. So same, these three filters we want to replace with this single filter, which is traditionally not possible using conventional. We need a MEMS, RF MEMS devices. So this was our part which we have done. So now what they are using right now. So currently discrete off-chip resonant components, which are quartz crystal, SAW devices and BAW devices, which are rightly now used in all our wireless communication systems. So why this SAW and BAW resonator filters are used is because they have a good quality factor, they have a wide tuning range, they have a thermal dependence, they have aging stability, and they have lower motional resistance. Now, this motional resistance is basically it is a resistance, but it is called as motional resistance because when hello, yeah, any issues? Hello.
No, sir. No, sir. I think
Okay.
someone from the participant unmuted their microphone.
Okay. Check. Yeah. So the motional resistance is basically whenever I tune my filter from one frequency to second frequency, the resistance, as you know that there are two types of resistance, the input resistance and the output resistance. So whenever I want to design any analog circuit, there has to be a resistance matching has to be there. And why this is? This is because of maximum power transfer theorem. As you know that if the input resistance and output resistance are equal, then the maximum power transfer is there from the source to the destination. So if I want to transmit the maximum power from stage 1 to stage 2, then you need to have this motional resistance. And as you know that the output resistance should be very low and the input resistance should be very high. So lower motional resistance. So lower means the output resistance should be less. And second thing, the motional resistance is that whenever I tune from one frequency to the second frequency, the resistance changes, and that resistance is called as motional resistance, and that resistance has to be less. Okay. And why this motional resistance is very less is because of the larger transduction area. Now, larger transduction area, as I told you, in case of accelerometer, we have moving electrode and the stable electrode or a constant electrode. So there is a area. So the area of that electrode, more the area of the electrode, you have a lesser resistance. So that is also called as transduction area, the overlap area between the two electrodes. So you need to have this lower motional resistance and transduction area. So these are some of the advantages of SAW and BAW resonator filters, and therefore currently SAW and BAW resonator filters are employed in our mobile phones and all the wireless communication systems that are used right now everywhere. So now, what are the disadvantages of the SAW and BAW resonators? So these filters are fabricated using ultra-fine machining and are bigger in size. So the problem is that these are bigger in size. So when we talk about miniaturization of electronic circuits and we want slim mobile phones, and then we want portable mobile phones, we want low power mobile phones. So since it is bigger in size is another problem. And the most important disadvantage of this is this: they are not CMOS process compatible. The meaning of not CMOS process compatible is because I cannot fabricate them using our CMOS technology, our transistor technology. As you know that transistor, like we are using now complementary MOS, CMOS technology. And why we are using CMOS technology is because it has very less power dissipation. So all the circuits, digital circuits that are designed are now were previously designed using CMOS process manufacturing technology, and right now we are using FinFET and all other technology. But a few years, 5-10 years back, we were using CMOS process, and these were not CMOS process compatible. And even this SAW and BAW devices are also not compatible with FinFET manufacturing processes. So basically, the manufacturing process of this SAW and BAW resonator is different than our integrated circuit manufacturing technology. Now, since they are not process compatible, so these are being off-chip components. Off-chip component means these are not on the chip, and what is not on the chip will be on the PCB. So the problem is that when I have a off-chip component or on the PCB component, then I need a PCB. I need a PCB and I need the entire interfacing circuit on PCB. So as you know that PCB cannot be miniaturized, so the size of the PCB is bigger. And whenever I have a PCB, there is a problem with the speed. There is also a problem with the speed because inside the integrated circuit, the speed is very high. And when it comes on to the PCB, the speed of the circuit becomes very low. For a simple example, I can give you in terms of our motherboard that we have a laptop on the in the laptop we have a motherboard, and inside the motherboard, you know that we have a processor i3 i5 processor which works at 2.4 gigahertz, but we have a RAM and we have DDR1, DDR2, DDR3 RAM. Now this DDR1, DDR2, DDR3 RAM works at 100 megahertz, 200 megahertz, and 300 megahertz. So they are connected on the PC. Now you can see the problem is that your processor which works at 2.4 gigahertz, but your RAM works at 300 megahertz. So there is a speed mismatch, and when there is a speed mismatch, then uh, you know that we have to work uh, with the compatible with the slow speed devices. So the speed of the entire system comes down. So therefore, we need to have a on-chip components. Okay, then miniaturization is impossible that I. Now, there is another major disadvantage is that it has a high insertion loss. High insertion loss, you know that whenever we have a processor, whenever we have a filter, so the output of the filter should be equal to the input, and it should only drop the frequencies which are not required, and it should select the frequencies which are required without attenuating the input signal. But this is practically not possible, and there is a attenuation, and this attenuation of the input signal should be less. But since in case of saw bore devices it is high, so your insertion loss is high, and to cope up with this you require additional amplification stages. So this insertion loss, you require amplification stages. That means you have more power dissipation because you required amplifier, you required more components, and then your portability or your slim is again wiped out. And this again adds to your power dissipation. So these are the disadvantage of SAW and BAW resonator filters which are currently employed in our wireless communication systems and which can be replaced using
No audio, sir.
Uh,
uh,
yeah, it is back on track,
fine.
sir. No issue. Yes, sir. Fine.
So now, okay, so disadvantage of SAW and BAW resonator filters. Now, next is now when we have this MEMS technology, there are certain activation schemes which are used in case of MEMS technology, and which are called as electrostatic activation, piezoelectric activation, magnetostatic activation, and thermal activation. So the piezo electrostatic activation, which is also called as capacitive activation. So in this, what we have is an input signal, and there is an output, and this is a hanging electrode, and there is a below is a input electrode or bottom electrode, and there is a top electrode. So whenever I apply a voltage to this bottom electrode, then because the effect of electrostatic force, this upper electrode is pulled down and then it touches this output. Okay. So this becomes like a switch. So input, then this top electrode, it touches to the bottom electrode, and so the switch is connected. If I remove the voltage, then this, because there is no electrostatic force, because of the spring action, this upper electrode will again bounce back to its original position and it will be disconnected on and off depending upon the voltage applied to the bottom electrode. So this is bottom electrode, this is upper electrode, it forms a capacitance. So it is called as capacitive activation, or because it works on the electrostatic force, it is also called as electrostatic activation. Now another one is a piezoelectric activation. So in case of piezoelectric activation, this upper electrode will be like a piezoelectric material. So whenever I apply a voltage to this piezoelectric material, it will bend, and whenever it bends, it touches to this output. So with the use of piezoelectric material, I can connect the input to the output. So that is called as piezoelectric activation. Another is using magnetostatic force. As we have electrostatic force, we also have a magnetostatic force. So magnetostatic force, you know that there is a transformer, and in the transformer there is a coil and there is a magnetic core, and using Lenz's law there is a force is generated, and that particular force that particular force also is used to generate voltage in the secondary. Now in this case, if this particular bottom electrode can be replaced with the coil and the core, like iron core or toroidal core kind of material, and I can generate a magnetic force. That magnetic force can pull this upper electrode and touch to the output electrode. So that is called as magnetostatic activation. The last one is a thermal activation. Now, in case of thermal activation, what I will do, as you know that the power dissipation is directly proportional to the I square R, that is the square of the current into the resistance. So if I apply the current to this and I heat on this upper electrode, and because of heating effect, then this particular uh, upper electrode will bend and it will touch to the output electrode. So these four kinds of activation mechanism are being employed in case of RF MEMS devices: electrostatic, piezoelectric, magnetostatic, and thermal. Now, from this particular chart or from this table, you can see that what are the different specifications for electrostatic, thermal, magnetostatic, and piezoelectric. Now, the most important point what we talk about is the current. Now, why we talk about current is because if the current is zero, then the power dissipation P is equal to V into R. So, if current is zero, then the power dissipation is zero. Now, in case of electrostatic, now slightly this is of older data. So right now the voltage which is written here 20 to 80 volt. Now it is very less. It is 2 to 5 volt. So this 20 to 80 volt voltage is required to apply to this bottom electrode, so that this upper electrode is pulled down and it touches to the output. So this is slightly old data. Now it is 2 to 5 volt. So 2 to 5 volt can be applied here. And the current, now why there is no current flowing from this upper electrode? Because I am applying voltage to the bottom electrode. This bottom electrode has nothing to do with the input. It has nothing to do with the output. And since there is an air gap between the bottom electrode and the top electrode, so the no current is flowing from bottom electrode to the top electrode. Therefore, the current is zero. So the only voltage is applied, no current is flowing. So current is zero, power dissipation is zero. The size that we are in micron, so it is small size. The switching time is around 1 to 200 microsecond, and the force that it generates is almost 50 to 1000 micronewton. Now, if I am using thermal activation mechanism, then the voltage is 3 to 5. The current it generates is 5 to 100 milliampere, and therefore there is a power dissipation. The size is very large, the switching time is also very large, and it also generates a very good force. But the problem is this power dissipation. Because the current is flowing through this, then there has to be a power dissipation. So, which is the biggest problem. In case of magnetostatic, again, since it is a coil, and this coil consists of toroidal core or an iron core, and the current has to be flowed through this coil. If I want to generate a magnetic force using Lenz's law, then as you know that this Lenz's law, the magnetic force is proportional to the current. In case of electrostatic activation, the electrostatic force is directly proportional to the voltage. So now, because in case of magnetostatic, the force is proportional to the current. So you require significant current, and then you require significant power dissipation, and then the force and whatever it generates. Then once you come back to the piezoelectric material, again in case of piezoelectric material, the current is zero and the power dissipation is zero. So from these four particular electrostatic mechanisms, from these four different activation mechanisms and the table, it is clearly seen that the electrostatic and piezoelectric has almost zero power dissipation, zero current, zero power dissipation. So from this it is clear
Sir,
that since yes, hello,
excuse me, sir.
yeah,
Hello, sir. Hello, sir.
yeah, please.
Sir, was you are mentioned here switching times, sir. What do you mean by switching times, sir? Here, if operating the switch or process of
Operating the
starting, sir?
switch, like if I no, 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 like right now this is a just a simple example of switch. So if I apply the supply or something to the bottom electrode, the time it will take to connect to the output, that is a
Okay,
switching
sir.
time.
Okay, sir. Thank you.
So, so from this, it is clearly understanding that the electrostatic and piezoelectric activation mechanism can give you zero power dissipation and zero current. So, therefore, now the problem which remains is with the switching time and the contact force. So that can be later on using different designing techniques. You can reduce this switching time. You can increase the contact force. So that can be researched, and those problems can be solved using different kinds of designs. Now the problem with thermal and magnetostatic is that thermal you have a very large power dissipation, so that is ruled out. Then magnetostatic, even though magnetostatic, the problem is you need a core, and you need an iron core or you need a toroidal core. So therefore, the problem is when you want to fabricate using integrated circuit manufacturing technology, then this toroidal core and iron core, then it becomes very difficult for fabrication. So therefore, magnetostatic is also ruled out. So the most compatible with integrated circuit manufacturing technology is electrostatic activation, and electrostatic activation is the best one because of the voltage requirement and because of the power dissipation. Piezoelectric material is only used in case of typical
கொஞ்சம் லோட்
applications.
ஆகுது சார்.
Hello, hello,
அதை எடுத்து வச்சுக்கணும், ஓப்பன் பண்ணி வச்சுக்கணும். ஓப்பன் ஆக மாட்டேங்கி, கொஞ்சம்
hello.
சிரமப்படுது. ஹலோ,
Hello, can you hear?
No, sir. I think some Gopalan has accidentally started the mouse
Okay,
microphone. Yeah.
okay.
Sorry.
Thank you. I thought somebody has some questions to ask. So, okay. Can I continue? Okay. So now this piezoelectric, as you know that piezoelectric also a problem because you need a piezoelectric material for that. Now silicon, and then silicon p-type, n-type silicon, silicon dioxide, silicon nitrides, and metal, copper metal, aluminum metal, nickel, and so all these are standard materials which are used in case of integrated circuit manufacturing, and which are compatible with each other. So therefore, whatever you want to design, you should design using these materials. So again, piezoelectric, PZT or aluminum nitride, some kind of different materials have to be used. And so therefore, piezoelectric is also used only if it is required in some kind of applications. And if you can avoid piezoelectric, you should avoid piezoelectric. The point is that only if required, you can go for piezoelectric. So the most famous and mostly applied activation mechanism is this electrostatic activation, which is also called as capacitive activation. So now I will talk about my work which we have done. So the motivation was this RF MEMS capacitive resonator, A resonator is a filter. So capacitive resonator can be embedded in a variety of integrators that result in higher level of integration and low cost batch fabrication process. So high level of integration is because we are using traditional circuit manufacturing process. So integration is possible, and low cost batch fabrication because I can fabricate electronics as well as MEMS devices using same technology. So the cost of manufacturing is low because I don't require any specific machine. I don't require any specific material to be added. So since it is a usual process, so there is no problem with that. So CMOS process compatible, most important that whatever CMOS we have technology for fabric design of digital circuits, so that is compatible with that. And most important, and this is very important point, is that means in case of magnetostatic or in case of thermal or in case of what we piezoelectric, the most important advantage of capacitive silicon resonator. Capacitive means using electrostatic activation mechanism. Are the can be slightly tuned by changing the DC bias voltage that is required. Now, where is this DC bias voltage? So this is a bottom electrode, and I am applying voltage to this bottom electrode. Now, what happens that so this voltage which is applied to this bottom electrode, which is a DC voltage, which cannot be AC voltage, it has to be a DC voltage because you want to pull that switch down. So if it is a AC voltage, then it will resonate up and down, up and down. So the DC voltage has to be applied. So this is called as DC bias. Now, so what happens this DC bias change in the DC bias is required because of operation post fabrication fine tuning and temperature compensation of the resonator. So what all these three means is that what happens is, let us say I want to fabricate this upper electrode and my dimensions are, let us say 10 micron into 100 micron. But when I fabricate this, so what happens? It fabricated as 9.5 micron and 99 micron. So I wanted to make it 10 micron, but it so happened 9.5 micron, and I wanted 100 micrometer. Now it became 99 micrometer. So I wanted to apply, let us say 5 volt. Now because of that, now it has reduced to, let us say 4.9 volt, because the dimensions of the upper electrode has reduced because of the fabrication issues. So therefore what is happening is, now the 5 volt which is required to pull this down is now reduced to 4.9 volts. So now this DC bias has to be reduced to 4.9 volt. So therefore post fabrication fine tuning is possible using this uh, capacitive silicon, that is electrostatic activation mechanism. Then temperature compensation of the resonator. Now, generally what happens is that, as you know that, let us say if you have a normal room temperature, and if it is working at normal room temperature, then there is no problem. But let us say if you are using it to some another application and where it is heating at 300 degrees Celsius or 400 degrees Celsius. So if it is heated at 300 or 400 degrees Celsius because of the presence in the environment itself. So what is happening is that because it is heated, there is a slightly, it will bend. Slightly it will bend. It may not bend 100%, but slightly it will bend because of the presence of the environment. So now, since it has, because of the heating effect, so the voltage which was required 4.9 volt, now it is only 3 volt is required to bring it down to touch to the output electrode. So therefore, temperature compensation of the resonator. So electrostatic is possible because you need a temperature compensation. So whenever in such kind of applications where your MEMS are used in case of some another environment where the temperature is very high, then you can do temperature compensation in case of electrostatic activation. But you cannot do in case of magnetostatic, or you cannot do in case of thermal, is because it depends upon the current, and the current will flow whatever, depending upon the resistance, the current will flow. So the change in the forces is not very practical in case of other activation mechanism as compared with electrostatic activation mechanism. And then you have a practically zero DC power. That is another advantage what we get in case of electrostatic. So why we have practically zero? Because the bottom electrode and the top electrode are not connected. So that is the biggest advantage. So now the problem's definition of our work was the to design a dual frequency capacitive transducer resonator to provide low power consumption, CMOS process compatible, no spurious mode, and thermally stable solution for dual band pass filter and dual frequency oscillator applications in multi-band wireless communication system. So as I told you that we have uh, three different applications such as Bluetooth, Wi-Fi, and uh, GSM. So you need three different filters. So instead of three, you can replace with the one particular filter. So still now there is no such devices available. We tried for dual band. So instead of going for three different filters, if we can replace two filters with a single filter. So therefore, that was our problem statement. And so to design a dual band pass filter, where we have, you know that we have a band pass filter where the band is only single. So you have a pass band and you have a stop band, but you don't have two stop bands or two band pass, two band passes. Okay. So we wanted to have dual band pass filter and dual frequency oscillator applications. So for this six design strategies we applied, that was two-port electrical configuration, low loss structural material, array design, mixed electrical and mechanical coupling scheme, sub-micrometer transduction gap, and large transduction area that we have applied. And because of this, all these six design strategies, we got as achieve dual band pass filter, narrow pass band, desired bandwidth, low insertion loss, better stop band rejection, and better thermal stability. So this was our problem statement. This was the strategy that we applied, and this was the expected output, or what we thought that this should be the result of the our strategy. So this we have done. So let us see now. So now, if I want to design, now CC is called as clamped beam. So you have a beam, and a beam is clamped at both the ends. So it is called as clamp beam. So if the beam is clamped at single end, then it is called as clamp, and if on the other side it is free, then it is called as CF, clamp free beam. Now there are free beam also, that they are free on both the sides. Okay, so they are virtually hanging. Now practically it is not possible, but through design it is possible. So practically they are free on both the ends. So these are the different types of beam design. So now, as per Euler-Bernoulli's equation, that these are the frequency of the beam, which depends upon the Young modulus, the density of the structural material, and beta n is the mode coefficient. So whose value for are given in this way, and T is the thickness of the beam, and L is the length of this beam. So now, according to Bernoulli's equation, then the length to the width ratio and length to thickness ratio has to be large, and it should be typically greater than 10. So if you want this frequency equation to be applied, then just a second. Hello. So,
Yes, sir. Please.
if you need this frequency equation, Euler-Bernoulli's equation to be applied, then the requirement is that the length to width ratio and the length to thickness ratio should be greater than, typically it is a 10, it should be greater than 10. So then we have a coupler. I will I will go to the diagram first. Okay. Now, this is a device structure, which is a MEMS resonator or a MEMS filter, which consists of four clamp beams. These yellow colors are the clamp beams, and which are attached to the anchors. So 1, 2, 3, 4, and 1, 2, 3, 4 are the anchors, right? And we have these four beams. Now these four beams are connected with the coupling beams. So these black color are the coupling beams, this black color, and these were identified. I mean, the position of these couplers are being identified through some experiments. So this is at this position, and then this is connected at the center. And these blue color are the input electrodes. The green color is the input electrode, and the blue color is the output electrode. So the position of the input electrode is at the center, and the position of the output electrode is on these two sides of the clamp beam. So because there are four beams here, it is called as array structure. Now these array structures are coupled, means this is not an independent beam structure. So these beam structures are coupled using these couplers. So this was the structure that we have designed for resonator application, for dual band resonator application. So now we have decided the frequency of this. So the frequency is given by this Euler-Bernoulli's equation. Now I want to design this mechanical coupler, that black color mechanical coupler. Now this black color mechanical coupler can be designed where now using these equations. So where B is your bandwidth, whatever bandwidth is required, Kc is the stiffness of the coupler, and Kr is the stiffness of the resonator point at X. So the point X is basically where the couplers are attached to the beam. Right? So using these three equations, B, and then you can find out the stiffness coefficient of the coupler, where omega is the frequency, Wc is the width of the coupler, P is the thickness, and E is the Young modulus, and rho is the density. So the length of the coupling beam corresponding to the quarter wavelength. Now, this quarter wavelength is very important point here, is that now if you are designing for a particular frequency, then you know from that frequency you can find out the wavelength of the signal. Now one point you have to be very careful here is that you know that the relationship between wavelength and the frequency is the speed of light, right? Or the speed at which the signal is moving. But you know that the speed of light, which we technically take during our whenever we teach or whenever we calculate, it is the speed of light which is in vacuum. But the speed of light or the speed of signal in particular material is different. So like if you have a copper wire, the speed is different. If you have aluminum, the speed is different. If it is a semiconductor, the speed is different. So whenever you are calculating the wavelength, then you need to be careful. You have to find out what is the speed of the signal or the speed of that particular frequency in material you are using. So if you are using nickel, or if you are using copper, or you are using aluminum, you have to find out that. And then based on that, you can find out the quarter wavelength. And so the length of this coupling beam can be given by 1 upon 4f. So 1 upon 4f is the quarter wavelength, and which is given by, again, using Young modulus and rho density. So as I told you that the couplers, the black color couplers were connected to the CC beam, and those node points were identified. Now to minimize this energy loss, and coupling beams were coupled to the CC beam at equal velocity node points when operated in mode 1 and mode 3. So now what happens, you know, see, whenever there is a pendulum, not about pendulum, but like if you take a rope in your hand and you tied a rope to something else, and then you just vibrate that rope, right? So it generates like a sine waves. It generates some sine waves. So these sine waves has some node points where the displacement is zero. So now whenever you are vibrating that particular row, so it vibrates in different, like we have harmonics. In case of electronics, we have harmonics. So every signal has different harmonics. Like if I take a power signal, which is at 50 hertz, then it has harmonics at 100 hertz, 150 hertz, 200 hertz, which are multiples of that 50 hertz frequency. So similarly, in case of mechanical domain, whenever I have any particular beam, or then and if I vibrate that beam, it also has some harmonics, and those harmonics are called as mode 1, 2, 3, 4, 5, and so on. So whenever these beams vibrate in particular mode 1 or mode 2, then it has zero displacement points. Okay, and now there are 2 points. There are zero displacement points and there are equal displacement points. Okay, so whenever the two ropes are vibrating at the same frequency, then they have equal velocity points. So these equal velocity node points were identified. So these node points were identified at this particular and at the center position. So you can see here, this is a dark blue portion and this is a dark blue portion, which clearly tells you that the velocity of this point and this point is zero, and the velocity at this particular point and this particular point is same or equal. Okay, so these equal velocity points were identified. And once these equal velocity points were identified, then those couplers were connected. So you can see here, so this is our input electrode and these are two blue color are our output electrode. Now this is vibration is in mode 1. You can see this vibration is mode 1 and this vibration is in mode 3. So you can see this is a, like we have a sine wave. This is the first half or a positive half of the sine wave. And you can see here, this is a complete sine wave and then there is a half sine wave. So this brown is input and this blue are output. So this is vibration in mode 1. This is vibration in mode 3. So if I apply input AC voltage, now see here, as I told you that it should be a bias DC volt. Previously I told you the biasing should be DC volt. But if the biasing is DC volt, then it will not vibrate. Then it will, because of the electrostatic force, either it will pull down, and if you apply negative volt, it will go up, but it will remain in one position because it is a DC voltage. So if you want to make it vibrate, you need a AC voltage. So if I apply a AC voltage, positive, negative, half cycle, it will vibrate this in all modes, mode 1, 2, 3, every modes. Okay. So now this arrangement of input signal and output signal was basically electrical couplings. So what happens if the input, now you can see here current, you can see here current. So if the input current is in this fashion applied, then the output current IO1, which is from one output electrode, and IO2 from second output electrode, both are in phase. Both are in phase. Now, because you can see here, as if it is pulling down, then this is going up. This is going up. Okay, if this is going up, then this is coming down. This is coming down. So it clearly tells you that the phase difference between the input and output is going to be 180 degrees. So which is seen in the current also. So if the input current and the output currents are 180-degree phase shifted, but the output from the output electrode 1 and output from the output electrode 2 both are in phase, and if I add this, then I get enhanced output. So enhancement of the desired mode through electrical coupling was achieved in this case. Now here you have mode 2 and mode 4. So it is vibrating in mode 2, it is vibrating in mode 4. Now you can see here it is away from the output electrode, and here it is near to the output electrode. In case of mode 4 also, here it is near to the output electrode and here it is away from the output electrode. So therefore, the output current I01 and I02 are in out of phase with each other. So what is happening with this, because these are output out of phase, if I add these two current, it becomes zero because they are out of phase. So what is happening is suppression of unwanted. So we do not want mode 2 and mode 4. So suppression of unwanted and spurious modes. Spurious modes are unwanted mode. As you know that mode 1, mode 2, mode 3, mode 4, 5, 6, those are predictable. Means those are the natural harmonics of the material. But spurious modes are because of the noise. So because of the noise, there can be a sudden mode, or there can be a sudden harmonics, like in case of our power line signal, we have 50, 100, 150, 200 harmonics frequencies. So that is, it is going to be there because of 50 hertz. There will be a harmonics at 100 hertz. There will be a harmonics at 150 hertz. But because of noise, or because of lightning, or because of anything else, there can be a harmonics at 125 hertz also, or there might be a harmonics at 80 hertz also. So those are called as spurious mode. So you want to suppress those unwanted and spurious mode, which was done using electrical couplings. So connection, that means input electrode and two output electrode, and placing them in this particular fashion was the electrical coupling scheme. And using this coupler, those couplers which were connected at equal velocity point was the mechanical coupling scheme. So therefore, there were two coupling schemes, mechanical coupling scheme and electrical coupling scheme was employed in case of this design. So now device fabrication. So we have gone through the different governing equations that was used for the design of couplers, the length and the frequency, and then we using electrical coupling scheme and mechanical coupling scheme, we got the desired application. And now we want to fabricate. So these were the wafer specification. The silicon wafer which was used, was the size was 2-inch wafer, single side polished. Orientation was 100. It was an N-type wafer. So as you know that there are P-type semiconductors, there are N-type semiconductors, and there are pure semiconductors. So we employed P-type of semiconductors, and the resistivity of that semiconductor was greater than 1000 ohm centimeter, right? So depending upon the doping profile, so if it is heavily doped, the resistance will be less. If it is lightly doped, then resistance will be high, right? So then the material, so this we have used 2-inch silicon wafer. Then we required mask plate for lithography. Then we required oxides. Si2 was used, silicon dioxide was used. The metals was chromium, gold, and nickel was used. Then for different depositions and removal of the unwanted material, acids were used, and those were acetone, IPL, PG remover, and 5:1 BHF. Okay, and the photoresist that we used was this AZ5216. These are, and this is a LOR, which is used in case of removing of the. There are, okay, we'll come back to that point in the next slide. So these were the materials that was required for fabrication, and this fabrication was done at IIT Bombay. Okay, so this is the mask. This is a mask. Okay, so this is the mask number 1, which consists of connecting pads, anchors, and input-output electrodes. Now you can see here. This is the small device. This is a small device, right? So these are the anchors. These 4 dots that you can see. Those dots are nothing but the anchors, and then these are the connection to the anchors. This center is the input electrode, and then these 2 are the output electrodes. Now you can see here the device is very small, and these are the connecting pads that are required. So these are so much, the space required for connecting pad is so much, because whenever we want to test our devices, then the thickness of that is almost 50 or 150 micron. So you can see the pattern which was used was GSG, that is ground, signal and ground. So GSG. So for RF input signal, because this is an input and this is the output. So AC input was ground signal ground, and the output was also ground signal ground, GSG. It is, in short, it is called as GSG. And for this anchor, we have applied the voltage. DC bias is required. So there were two provisions were given to apply the DC bias. So you can have the provision of application of DC supply on the left hand side also. You have a provision to apply DC voltage on the right hand side as well. So there is a prober machine is required which can directly probe into your integrated circuits. So in that particular prober machine, depending upon your connection, you can probe from the left hand side, you can probe from the right hand side also. So alternately, you require both the methodology. Sometimes if you cannot connect from the left hand side because all the probes are being utilized for something else, you can connect from the right hand side. And this is a DC, positive DC, and this is ground connection. So all the grounds were connected. You can see all the grounds are connected, and this is AC input, this is AC output, and this is DC positive input, and this is ground. So this was mask number 1. Then this is second mask. Second and third mask was similar. I will talk this in next slide. So these are for anchors. So these are for anchors. You can see these are anchors. And then this is the fourth mask, right? So which is a CC beam. So these are the clamp beams, and these are the coupler beams. Okay. So which were fabricated at the single go in one moment we fabricate. One moment means one single layer. Okay. So now this is a device fabrication process, how we did this. So in the first case, we have an N-type silicon substrate. On this N-type silicon substrate, yeah, first of all, you need to select the substrate, N-type or P-type or pure semiconductor. Then you have to resistivity, whatever you want. And then you need to clean this silicon substrate. So there is a RCA cleaning process. A standard RCA cleaning process is applied for cleaning of this silicon substrate to remove all the particles or whatever dust you have accumulated on the silicon substrate just because it was lying in the shelf. So that is the reason. Now on the top of that, the first is the deposition of silicon dioxide. So the standard dry oxidation or wet oxidation process you can use for deposition of SiO2. So if you want a very thick SiO2, so now this is a 2-inch wafer, and this 2-inch wafer generally 100 micron is the thickness of this wafer. So if you want 10 micron or 20 micron of this SiO2 to be deposited, then you need to go for wet oxidation process. And if you want to deposit very thin SiO2, like only let us say 100 nanometer or 200 nanometer, very thin oxide, then you can go for dry oxidation process. So SiO2 has to be deposited. It is an insulator, and if you do not want connectivity of this P-type, N-type substrate to the top metal layers, then you can use this SiO2. And if you want connectivity, you can remove this SiO2 and it can be connected to the N-type substrate. That is all. Okay. Then in this case, now I wanted to deposit this first. I wanted to deposit these connecting pads, base of the anchors, and input-output electrodes. So this was the first metal that has to be deposited. So first stage. So now in this case, what is happening is that I want to deposit a metal. Now the metal layer, you know that because it is a connecting pad, this first one is a connecting pad. So the connection has to be made with the outside world. Like with your measuring, you want to measure with CRO, you need to connect function generators, or you need to connect this noise analyzer and so many things. So it has to be connected to the outside world. So therefore, the connecting pad, the material used in the connecting pad is gold material. So now the gold does not directly stick to the silicon substrate. So you need to use chromium. So now the first I wanted to deposit these connecting pads. So now as you can see here, I want metal, this white portion has to be metal layer, and this black portion I don't want metal. On this black portion nothing is to be there. Okay, and white portion should be my metal. So now I want to remove this metal from the black portion. I want to remove the metal from this black portion. So what we did is we deposited, we have used, in case instead of using etching, we did lift off process here. So in lift off process, what happens? First I deposited this photoresist, which is LOR and AZ5216. Now the desired thickness, now let us say if I want the thickness to be let us say 100 micron, then I must deposit this photoresist with at least 300 or 400 micron thickness. I am talking about thickness. So, and the X and Y size is going to be according to your devices. Now this is a 2-inch wafer, and the standard size of this is around 500 micron by 500 micron. So on a 2-inch wafer, I can deposit as much as possible 500 into 500 devices. Right? So we deposited photoresist, and then we removed this photoresist wherever we wanted to have connecting pads, wherever I wanted to have a metal, right? So this step 2 we deposited LOR, and then we removed this in the step 3, and in the step 4 we deposited chromium, and then we deposited gold onto this. Right now, as you can see here, the chromium and gold was deposited in this fashion, like this. So in the step 5, what we did is we removed this photoresist. So when I removed this photoresist, whatever was deposited, gold or chromium that was deposited on the top of this photoresist has been removed from here, and remaining is what I wanted. So the connecting pads and whatever I wanted, that is being kept here. Now the same process is again repeated for the second layer. So in this again I deposited LOR plus A25Z photoresist. Okay, now so this etching, this removal of photoresist was done using this mask tool, this mask. Okay, because I wanted to deposit metal only in these square, white square boxes, and I do not want to deposit metal onto this black surface. Okay, so hello, hello, hello. Hello.
Sorry sir, actually somebody must have परत by mistakenly microphone on केला.
ठीक आहे. नाही, त्याला काहीतरी म्हणायचं होतं वाटतं, काहीतरी. आय थिंक ही वॉन्टेड टू आस्क समथिंग. Okay, ठीक आहे.
Dr. G. Lakshmi, I think I have mute you. So if you want to ask anything, sir has stopped, so you can ask the question. नाही sir, maybe ते नाही करत unmute. You carry on, sir.
Okay, ठीक. So we removed the material for the anchor using mask number 2. Okay, then again we deposited the metal onto the top of this everywhere. So whenever you deposit metal, it will be deposited everywhere. So it got deposited here, it got deposited on the top of the photoresist. So again same, we removed this photoresist, this purple color photoresist was removed, and we got this kind of structure. So these are your connecting pads, and this is your anchor. Okay, this is your SiO2, and this is your substrate. So again, now in the third layer, now the problem is that is because now what is happened, in this particular ninth step, now I want to deposit metal. I want to deposit metal on the top of this anchor, and here this position there should be air gap. I want an air gap in this. So now I want to make this air gap there. So we deposited SiO2 here. So as you know that if I want to deposit, it will be deposited on the complete wafer. So we deposited SiO2, and to remove this SiO2 from the remaining part, only we wanted here itself, below the our beams. So then we again applied this photoresist. This photoresist was removed. Okay, and then from this we removed this SiO2 from this part. So from the here you can see SiO2 remained only on this particular surface, and on the top of this anchor SiO2 was removed. So from this we have a window here. So this window was made to remove this SiO2 from this part windows. So at the end we got this removed SiO2 from here, and SiO2 was there in this part. So then again, now this is another fourth layer. So we followed again, we did photoresist deposition. We etched out this photoresist. Again we deposited chrome and gold here. And then after deposition, we got this particular output, and then we removed this photoresist from here. So after removal, this is called as lift out, because I am removing this, so it is lifting out whatever is on the top of the photoresist. So after I remove this, I got this kind of structure. So the SiO2 is here on the top. This is my beams, coupler beams and the CC beams. These are the anchors and these are the connecting pads, and this is the SiO2. And finally, I removed this SiO2 using BHF solution. So the entire SiO2 was removed from this. Okay, and then I got this finally hanging structure. So so this is the actual chip. If you see through the microscope, this is what you can see, the silicon structure. So this is the complete silicon chip, and this is enlarged. You can see these are the connecting pads as it was there in the mask. And if I enlarge this, these are the 4 beams. So this is beam number 1, 2, 3, and 4, and these are the beams. These are the coupler beams, you can see in the gray color, and in the below you can see there are the input and output electrodes. So at the center we have input electrode, and at the other end, left and right, you have output electrode. So since you can see the input and output electrode clearly from this, it shows that the SiO2 from this particular portion was completely removed. So this is the actual photograph of the chip that was designed, and you can see the difference, the gap between this upper electrode, that is the CC and the coupler beam, and our bottom. So the gap between these two is measured, and which is around 387 nanometer. So the gap between these two was 387 nanometer. As I told you that we need this gap should be as small as possible. If you want to have low motional resistance, that means the output resistance of the resonator or the filter should be very less. So for that you have two things. One is that the gap between the upper and the lower electrode should be very small, which is 387 nanometer, and the transduction area, that is the overlapping area between from the input, and now this is my resonator on the top, that is beams. So the overlap area of the input and of the output overlap area is larger. So it should be larger, area should be overlapped, and this gap should be small. Now if there is a single beam, if there is a only single beam, you can see the area, the overlap area of input and output will be very small. But now because there are 4 beams, so the area, overlapping area is as compared to the single. So this is the photograph. And then these are the physical parameters that we measured through. So beam length, beam width, thickness, electric to resonator gap, coupling, everything was designed and then measured also. Okay, so young modulus, density, Poisson's ratio, everything was measured. And then these were the electrical parameters that we measured. So this is the uh, capacitance, DC voltage, resonant frequencies, bandwidth, input power, output power, what is the transmission, and everything for mode 1, and then for mode 3. So it was measured, and then the graph was plotted. So this is a simulated graph. So if with this you can see mode 1, you can see mode 1 frequency response, mode 2 frequency response, mode 3 frequency response, right? And these are called as spurious modes. So these are called as spurious modes. So these spurious modes, this is when wideband frequency response without mechanical and electrical coupling scheme. So you can see all those modes, and there are spurious modes also. This is without coupling. And then after you couple, so wideband frequency response with mechanical and electrical coupling, you can see mode 1 and mode 3. So mode 2 is almost zero. Then spurious modes you can see are almost very less. The output of mode 3 comparatively has reduced. So you can see here mode 3 is so much, and in this case mode 3 was very less. So uh, this is the output which we plot using network analyzer. So on the network analyzer, you have the frequency response. So on the network analyzer, this was plotted, which shows you the power, output power in dBm. It tells you the frequency, it tells you the bandwidth, it tells you the power, and it also tells you the Q of this. So this is mode 1 response, which was measured, and this is the mode 3 response, which was measured. So you can see the frequency, you can see the bandwidth, and you can see the power. So this we demonstrated the operation of mode 1 and mode 2 in a single, mode 3 in a single device. So this is dual band operation where all other bands were suppressed. Only we got the output at the 2 different bands. And then this is the temperature compensation, where you can see almost from this, you can say 20 degree to 60 degree, it is a flat curve for mode 1. And even for mode 3, it is a almost flat curve for the normal temperature, normal operating temperature of 20 to 60 degree. So we compared our results with different papers that were published in IEEE, so 2015, 2012, 2017, and then our work. And this is the comparative that we have done, right? So you can see the DC voltage, you can see is almost 5 volt was required as compared to 18, 150, and 30 volt. Then they have used aluminum structure, aluminum. Then we have used chromium and nickel as a bilayer. Then there was a capacitive. Our was also capacitive. It was CC beam, clamp beam. Here it was free beam. Then there were ring and seesaw type of. Then bandwidth control was the main this one. Bandwidth control was not there, but we had a bandwidth control. As you can see in the governing equation, there was an equation for B, and the bandwidth can be controlled if you control the stiffness, and the from the stiffness you can decide upon the coupling points. So basically, if I change the coupling points, then I can change the bandwidth. So this bandwidth control was possible in our case. Then so these are all Q, which is measured in vacuum. So slightly it is larger because we measured Q in air. So it was 133 and 130, approximately 130. This is the transmission power, output power, and the frequencies that was measured. So this is a comparison of all this work done from the IEEE transactions. And from the conclusion, what I would say is that the dual frequency resonator may be actively considered for deployment of dual band RF and IF signal filter and oscillator application. CC beam can be explored for dual frequency operation for mode 1 and mode 3, and whereas mode 2 and 4 vibrate in out of phase mode. So as I shown you in the current output, mode 2 and 4 vibrate in out of phase, while mode 1 and 3 in phase. Then vibration amplitude reduces the at higher resonance mode. Therefore, higher frequency band mode 3 may observe slightly more insertion loss as compared to lower frequency band. So as I showed you in the output also, for mode 3 the output was very less, and for mode 1 output was more than mode 3. So if you go for mode 5 and if you go for mode 7, then output will be very less. So therefore, we discourage not to go for mode 5 and mode 7. Then 6 design strategies that I have discussed previously. So sub micrometer transduction gap. As I told you, sub micrometer transduction gap was that 387 nanometer gap, and large transduction area, as instead of having a single beam, we had 4 different beams. So therefore, the transduction area was very large. And electrical configuration and coupling scheme and mechanical configuration, array design, everything was the strategy that we applied was very successful in this. So in general, what I would like to conclude is that the MEMS industry is very big, it is growing, and therefore everybody should look into this, and all the colleges in their respective engineering colleges or science colleges, they should go for MEMS as a core subject rather than going for an elective subject. So because we need a lot of manpower in this MEMS technology, as we have missed the bus of integrated circuit manufacturing, but at least we can become the major manufacturer in MEMS sensor technology. So adoption of MEMS technology is right a problem right now, because now you will ask me why MEMS sensors, why these there are so good there are so good results, then why this technology is not in our mobile phones and everywhere, is because all these mobile phones, they have standard manufacturing processes, and if they want to integrate MEMS into that, then they want to change their manufacturing line. And with this the mobile phone sales, and they are in a hurry to launch the mobile phone. So right now they are not considering it as worth changing. And as you know that mobile phones, the cost is also lowering every day, so they don't want to take it that technology innovations is required. You need to find out different solutions to innovations to answer for measuring all other parameters like blood pressure, blood pressure, or you want to measure RBC, or you want to measure temperature, or then there are so many, like now environment is a problem, this toxic gases is a problem. So all this you need a technology innovation. You need to design some innovative products that will take case. There is a strong market for wireless communication system, mobile phones, and GPS. And focus on product. If you are going for entrepreneurship, you have to focus on product. And if you want to go for or otherwise, there is a manpower development is required, so that everyone should take care, so that there is a job opportunity. And then means all our electronics graduates and postgraduates should get somewhere placed. So if we have a MEMS sensor industry in India, definitely they will get a job into this. So that is an important point. And before going to the next slide, I can take some few questions. The organizers allow us to.
Yes, sir,
Sir,
definitely.
good evening, sir.
Good evening.
Hello, sir.
Hello.
I'm
Yeah,
audible,
please.
sir.
Yeah, audible.
Sir, it is not a question, sir. Question and appreciation.
Yeah, please.
Sir, I am a Dr. S. Madhav Reddy, Mahatma Gandhi Institute of Technology, Hyderabad, sir.
Okay.
I'm working in a professor of mechatronics department. We have mechatronics branch in our college.
Okay. Okay.
We have a core subject for MEMS subject, sir.
Very good. Very good.
This subject actually since 2012 There are 7 batches already passed out, sir. They studied MEMS subject.
Okay.
But I am a teacher for that taught the subject for
Very
students.
good.
Actually, basically we are mechanical engineering. We don't know this much knowledge regarding RF MEMS, all this. So, but we have one chapter in RF MEMS, sir. But only basic level only we tell to the students actually. Generally, thank you very much, sir, for giving me joining for this subject for MEMS technology, RF MEMS, and the MEMS technology used for sensing and actuating. And actuating methods also explained very nice, sir. And with your project
Thank
work
you.
and your research work you explained here, I felt very happy, especially. Why? Because I know the subject a little bit.
Thank you.
One more
Thank
thing,
you.
sir. Generally, the resonators were selected CC beams or all this, sir. But I studied only hollow chamber. When the designing of resonator, you go for hollow chamber. So, what is the difference between rather than this hollow chamber, you have chosen this CC chamber, sir? Anything you can achieve? Any benefits, sir, for this?
See what is there are different kinds of different ways. So like you said, hollow chambers are there. Then there are CC beams. Even there are square plates, circular plates. So people are actually doing some research using different kinds of materials, different kinds of designs, and then whatever they have. Like now in our IIT Bombay, we had multi-layer manufacturing. So we did multi-layer manufacturing. So depending upon the manufacturing process, depending upon the applications, you can select anyone like hollow chamber, you can select CC beam or square plate. So it totally depends upon the application and the manufacturing facilities at your end. So I think there is nothing as such any positive or negative about any particular material or any particular shape or size. It totally depends upon application.
Okay, sir. Thank you very much, sir. Thank you so
Thank
much.
you. Thank you.
And a very great privilege to sir. You have given a very nice presentation about RF MEMS. Actually, most of the faculty, all participants are background in mechanical engineering here. And
No.
what you are
So now
explaining
what
there.
I want to add into this now. See, basically, you should not only relate this with RF MEMS. Basically, the point is that it is a fabrication technology, and using this fabrication technology, not only RF MEMS but any kind of MEMS sensors can be designed. So, as you have seen, there was a repetition of fabrication steps. Like step one, we did
Yes,
photoresist
sir. Yes,
deposition,
sir. You explained
metal deposition.
photolithography techniques. You explained, sir. Very nice.
So the point is that only the mask design changes. So depending upon your application or depending upon your design, so only that mask will change. While the technology remains same, fabrication technology remains same. So like it is like a CNC machine. So how you program that CNC machine will be the output, shape or so basically, idea was to demonstrate the fabrication steps, what work I have done. So through that I have explained, and it is applicable for everyone. It is not only about
Yes.
RFM, but it is
Okay, sir.
applicable for everyone.
Yes. Thank you, sir. Thank you so much, sir.
Thank you.
Good afternoon, sir.
Good afternoon.
Sir, actually, the information which you are given is very, very nice information. I have one question that if the information which you are given is how to fabricate the given sensor, but directly we have if I want to build a MEMS sensor for my IoT application, so directly I have to have the manufacturing or some basic mathematics or some designing is required, or directly with the material I can build the sensor.
No. So no. You need to start from the basic point. Like you need to design. You need to have some mathematics. You need to design whether it will be a square shape or whether it will be a rectangular shape. What will be the thickness? Which material you are going to use? Whether you are going to use metal or you are not going to use metal, or whether if you are using copper, you are using aluminium, you are using gold, you are using chromium, you are using XYZ, or you are using piezoelectric. So everything has to be planned and for planning, you need to have a basic fundamental logic for selection. Otherwise, then it will go wrong everything.
So that means material study is also required and designing is also
So see,
required.
what happens, see, material study is not required basically, but from the Google or from the internet or from the catalogs of the different manufacturers, you can find out the specifications of different materials. So like what is the resistance, what is the melting point, or what is the young modulus. So now see, material research is so much that you need not do everything. You want to only select the material. See, whether you want to select aluminium or you want to select copper. So you need not measure all the specification properties of these metals. So you have a catalog from the catalog, but you should know that how much resistance you want. So if I want, let us say 0.00001 resistance, ohm, so then which metal I should select? Whether I should select copper or I should select aluminium. So you have to only in the catalog you have to only see that which material matches the resistance, but resistance has to be calculated by you.
Okay, but now I have designed some sensor. I have manufactured it and I have tested it. But when it comes to the large scale, it is possible to have the large scale production for that sensor so that it can be used by everyone.
Yeah. If it is a complete silicon manufacturing process you have done, then it is possible, because as you know that you have a 2-inch wafer, you have 4-inch wafer, you have 8-inch wafer. So depending upon the size of the your wafer and size of the device, you can fabricate 100, maybe 500, or maybe 1,000 devices on a single chip.
Okay, okay.
Then you need slicing, and then you need packaging that you have to do. Wire bonding you need to do, and then packaging and that.
It's MEMS manufacturing or testing available in India.
Yeah, it is available. Testing is available at most of the institutes. Means almost all IITs and maybe all those old NITs also available. In VNIT, all testing facilities are available. Only fabrication is available at IIT Bombay, ISC Bangalore, and then something can be done at I think IIT Kanpur also.
Okay, so that
See,
test
if you
that
are,
is
no,
available
see
only
what
through.
is, no, not manufacturing. See, all those IITs and NITs, those are actually experimentals. Means you cannot go there and do mass manufacturing. So those are for education purposes. So if you want to go for mass manufacturing, then you need to look at the foundries at Singapore or South Korea or Taiwan or China or USA, like that. Because if you want to do fabrication, means if you want to set up your own fabrication, it's a slightly costly affair right now. Means like only Tatas and Ambanis can go into it, or Wipro or TCS. But a small industry, because like now the prober which we have in our VNIT, it itself costs 1.5 crore rupees. So only one testing unit costs to 1.5. So if you want to have a, small fabrication facility of MEMS, it may around take you somewhere around 20, 25 to 50 crores. So that, but 25, 50 crore is not a very big amount. But means other bigger industries like TCS is there, Infosys is there, or Tata's, Birla, Mahindra, they can, I can 10, 50 crores are not too much for them.
Okay, okay, okay. Because of this IoT, there is a necessity of having this MEMS sensor to reduce the size and cost and the power
Yes,
requirement.
yes, yes. Yeah.
There
And
is a
not only about RF MEMS, you can have any kind of sensor for measuring any kind of physical parameter. Means anything. Like if you ask me, like let us say how much noise you have in your room, or how much toxic gas is there, or how much sulfur is there in environment, or what is my blood pressure, or what is my let us say body temperature. So everything means you can have MEMS sensors for this, and IoT is all about that only. Like tomorrow, maybe you can sit at home, connected all sensors, and already doctor knows that what is happening with you.
Yes, yes, yes. There is a huge potential in this particular area.
Yes, yes, yes. There is a huge potential, and right, that was I selected those applications which were based on optical, which were based on portable blood analyzer, and then inject printer head. So I just wanted to demonstrate that there are so much diverse kind of applications of MEMS.
Hmm. Hmm. Yes, sir. Yes. So you are given very nice information. Okay. Thank you, sir.
Thank you.
Sir,
Okay.
the MEMS sensor is omnipresent, sir.
Huh?
Everywhere. Omnipresent, this MEMS
Everywhere.
sensor.
Yes, yes,
Yeah, yeah.
everywhere.
Yes,
Yes,
sir.
yes.
Thank you, sir.
Sir, I would like to ask one question.
Yes.
Uh, how we can do some work on MEMS at our institutional level? Is it
See,
possible or?
yes, yes, definitely it is possible. So what you can do is that right now you have people from mechanical domain, and most of the mechanical domain people are aware with the software ANSYS. Uh, so this ANSYS software can be used to design those structures, like what are the modes, and whatever your mechanical simulations can be done using ANSYS software. And then at IIT Bombay, you can go for free fabrication. Means it is not free fabrication. They will pay you also. Means they will take care about your day-to-day lunch, dinner, and not only about that, but your residential also. So IIT Bombay, ISC Bangalore, and there are few IITs also where they have a scheme from the government wherein you have to submit the proposal. If your proposal is potentially good, if there is a logic in that proposal, they will invite you for fabrication. They will take care about your residential. They will provide you some space in the hostel. You can stay there. They can give you some 400 500 rupees DA per day, which you can use it for your lunch, dinner, breakfast, and they will provide you transportation also when coming to Bombay, going from Bombay. So typically it takes 3 to 6 months of fabrication, and
Okay.
so you have to be there in Bombay for 3 to 6 months. That is the only point. So you can do that, and means financially
Sir,
there is no burden on.
sir, any hands-on training at IITs
How hands-on training IITs regularly organizes STTPs and
on
all this.
MEMS
You can attend.
particularly?
Not only in I, even ISC Bangalore, IIT Kanpur, IIT Kharagpur, IIT Delhi. These are the centers where mostly MEMS technology. They are people who are working on MEMS technology at IIT Bombay, Kanpur, Kharagpur, Bombay, then Delhi and Bangalore. So in Bangalore, they have a multi-story building only for fabrication of MEMS devices. IC Bangalore.
No, we have to start from the scratch, you know. That's why I asked.
So
Because
no, no,
there is
no.
no.
You can start. So what you do is now. Normally right now when your normal college activities will start now, you can and if you have a MTech student in your MTech branch or a BTech, generally what happens, that much pain or that much time is not available with BTech students. But MTech, you have almost 1 year complete, or a PhD, you have a lot of time for that. So you can apply for a proposal at IIT Bombay. Then, if it is sanctioned, then you can go there and fabricate, and they will give you training also. That is not a problem. Means, in fact, if your proposal is accepted, you have to do first training. Then only they allow you to come inside.
Ah. The problem is for proposal also we should have that basic understanding first of all. Then only
नहीं
we can
आता
make a good
हाँ
proposal.
हाँ ना
Otherwise,
सो यू टेक
yeah.
यू ऑब्वियसली तर थोडंसं तुम्हाला अभ्यास करावा लागेल बाकी काही.
Acha. Okay.
Or I am there. If you have something, I will help you out. No problem.
Okay, sir. Thank you very much. Sir, any introductory book on that? To start with the MEMS.
Okay, so I will take next slide ahead. So if you have asked me the question of the book, so this is what with our work we got one patent is granted on our work, one SCI publication, one Scopus publication, and 3 conference publications at IIT Bombay, Hyderabad, and IIT BHU. And then book you want, so our book is also published by IIT UK on MEMS resonator filter. So in this book, I have 2 chapters which are based on the resonator designs. So this is also a basic book which you can use it, or there are lots of books now, MEMS, there are lots of books are coming. And on the next part, this is because I was belonging to the this tech, education industry, means educational institute. So this simpinfo.com site I have designed, which is available right now, which takes care about the architecture, engineering, science, and management domain, wherein you can find out the list of all good conferences, workshops, forums, fellowships, journal special issues, book chapters, and now we'll be having video lectures also on that. So we have presence all over India and other countries. Almost 10,000 visitors are there per month. You can post your event, like now you have an FDP. So this FDP can be posted at free of cost. We don't charge anybody for that. And all those reputed events are available. We have we have registration link also, wherein the faculty members or student can register on our website, and we provide them if something is FDP or some new conference is there, we inform them through WhatsApp or through email also. And we have registration from all the faculties of IITs, NITs, and IIMs also. So basically that is our plan, and only we charge if you want to advertise something which is not related with event and which is not related with conference, workshop, then we charge it. And so all of you can visit this simpinfo.com, and you can find out your conferences, workshop, your.
Okay.
And
Thank you.
finally, I thank organizers, the principal of the institute, the conveners, and all the coordinators, and last but not the least, participants for patiently listening and appreciating my presentation. So I thank everyone. And if you have any questions, you can always mail me or you can call me.
Yes, sir. Okay. Sir, Dr. Amol Morankar, sir, thank you very much for your nice presentation for last 2 hours. On behalf of NBN Snehagar School of Engineering and participants of this FDP, I thank you for sharing with us all this information in detail about MEMS sensors for automation, starting from commercial aspect, touching all the structural aspects and need of the MEMS throughout that is on indigenous level also.
Yes.
So indeed it was an interesting session. Case study of device fabrication was also discussed, and the results also were discussed with all of us. Thank you all participants also for your valuable interaction with sir. About tomorrow's session, let me ask Professor Nilesh Patil sir to make an announcement. Thank you all.
Yeah.
Nilesh Patil.
Thank you very much.
Thank you, sir. And regarding tomorrow's session, so we are going to start our session by 10:30 a.m. from Burane sir's, and then that will be taken over by the Adinath sir's session. Okay, so I request all of you to join at sharp 10:30 a.m. So we will start by 10:30 tomorrow morning, and links will be sent to you by emails and Telegram group. Okay, thank you. So. Okay. Okay. Thank you once again. So I'm closing this meeting. We'll meet tomorrow. Thank you. in the morning session.